This is our second lab report on air resistance and velocity by Ian, Jared, and Alexa.
A solid object moves to push fluid molecules out of the way. In this case, air is our fluid. According to Newton's third law, the object has to exert a force on the fluid to move through it, so the fluid exerts a force back on the object. The equation for drag force is half times the drag coefficient times the density of the fluid, pi times the radius of the object squared times the velocity of the object squared.
The goal of our experiment is to find a relationship between velocity of an object falling through a fluid, in this case air, and the resistive force, in this case drag.
We hypothesized that air resistance and velocity squared will have a direct relationship because based on the equation for drag force, the drag coefficient and the density of the fluid are both constant values, and the radius of each object stays the same as it falls, so then the only factor influencing air resistance will be velocity squared. Thus, we expect to see the air resistance grow linearly as velocity grows. And then we did confirm this hypothesis based on the linear slope of our velocity squared versus air resistance graph.
For the four objects we observed, we changed the mass and the radius of each object.
For our experiment, we used a small plate, large plate, bowl, and coffee filter. These four objects were massed and then dropped from 1 meter and recorded for position versus time and velocity versus time. From this data, we created a velocity squared versus resistance graph that will show the given relationship.
The three force diagrams show the object immediately after it is released, the object after it's been falling for some time, and the object at terminal velocity. So for all three diagrams, the force of gravity is the same, but the force of air resistance grows until the force of air resistance equals the force of gravity with no acceleration at terminal velocity.
Our system schema shows the objects we dropped having a gravitational force with the earth and a contact force with the air, which is also the air resistance.
We used our tracker data to create a velocity, centimeters per second, versus acceleration, centimeters per second square graph for the four objects. Terminal velocity is where acceleration is 0. So we created lines of best fit to determine each object's terminal velocity.
We calculated terminal velocity using the graphs on the previous slide, and then we found air resistance based on the fact that net force was 0, so acceleration is 0, and then air resistance just equals negative mass times the gravitational constant, and those were our values for that.
We graphed velocity squared versus air resistance and found the proportionality constant is the slope of the graph, which is 0.0246. As velocity squared increases, the amount of air resistance increases linearly.
Since Fg, or force of gravity, is equal to air resistance at terminal velocity for an object, we know that heavier objects take longer to reach terminal velocity, but their terminal velocity is greater. Also from this experiment, we discovered that surface area increases, air resistance will also increase.
We found that this relationship holds at terminal velocity, and so further investigation with heavier objects and recording for a longer drop distance would be necessary to verify that the relationship between velocity squared and air resistance is linear when we're not at a terminal velocity.
Some possible sources of error include the objects not falling straight down. They could have floated a little bit to the left or to the right, which may have thrown off tracker expecting a straight vertical fall. Also, the objects did not stay completely horizontal, which may have changed their surface area with respect to the ground and thus air resistance. One last possible source of error could have been we may not have dropped each object from exactly 1 meter.
The relationship between velocity squared and air resistance is the drag constant. This will not change no matter what the scale is. On macroscopic levels, we see higher velocities and higher resistive forces, but the constant is still the same.
G, and then once it reaches terminal velocity, the air resistance would equal the force of gravity, and a marble has a higher terminal velocity than a ping pong ball due to its larger mass, so then it would also experience a larger air resistance than the ping pong ball at its terminal velocity.